So, hello everyone. Hello to those listening us from the interwebs. Hello extension students, and hello guys. There's so many of you out here. It's so great to see such a great attendance for CS 152 sections. We have already posted the section notes and the section problems for this week. So today we're just going to be solving these section problems in detailed ways. And then if we have time left, you guys can ask questions about the homework or ask general questions about the class. And for those listening to us from online, please feel free to message us from Zoom, and then we'll be able to see your messages from there and respond to them accordingly. Okay, so we can get started on the first question of our section problems. So our first question has to do with the subject of induction. So in class we saw we saw axioms and we saw inference rules, and how we can apply these axioms and inference rules together to create new concepts. So for this example, we have two axioms. We have three rules total, and in these three rules we have two axioms and one inference rule. And as you can see on the screen, there's no need to write it. The first axiom just says that the number 8 is a member of the set QX, and the second rule says that number 5 is a member of the set QX. So those two are axioms because we have no premises at the top. But for rule 3, we do have two premises. Premises meaning that the conditions listed on top of the line as well as on the side of the line has to hold for the condition written below the line to hold as well, right? And for rule 3, that is if element A is a member of the set QX, and if element B is a member of the set QX, and C is equal to A plus B plus 1, then C is also a member of QX. So now with these rules, we can check to see if other numbers are a member of the set QX as well. So before we get started on problem B, let's look at problem A. So the rules above, rule 1, rule 2, and rule 3, which are axioms and which are inductive rules. As rule 1 and rule 2 do not have anything written on top of their lines, they have no premises. As such, rule 1 and rule 2 are axioms. Rule 3 has two premises written on top of the line and one premise written on the side of the line. Therefore, it is an inductive rule. So 1b says, give a derivation showing that 11 is in the set QX. So if we were to just write this again, QX is equal to like 8, 5, and A plus B, A plus B plus 1, where A and B are member of the set QX. Yeah. So if we want to see whether 11 is in this set, and this set can grow, by the way, so this is what this represents. What can we do? How can we get the number 11 from the number 8, the number 5, and this rule that we have set up? You guys know?
We can do 5, or we can do the A plus B rule, and then with the premise of A being 5 and B being 5.
Exactly, yeah. So in simple math, we know that 5 plus 5 plus 1 equals 11. So it's the same thing. A can be equal to 5, and B can be equal to 5 as well. And we just substitute into 1, and we get C. So now, in the homework as well, we will ask you guys to show this in a derivation setup in the tree. And so to do that, once you know the answer, you can work in reverse, because then it's easier to write. So we can see that at the end, we are applying rule 3. I'll write it right here. We are applying rule 3 with the condition that 5 plus 5 plus 1 is equal to 11. 5 plus 1 is equal to 11. And just to double check, yes. And so instead of writing this and overcomplicating it, what we can start with is the answer. So instead of this, we can just say 11 is a member of the set Qs. So how do we show this? Well, we have to apply rule 1, which is that 5 is a member of the set Qs. And rule 1 again. Sorry that went out, but we can just extend it like so. When you're typing this up in LaTeX, it does it automatically, so you don't need to worry about writing it. Yeah, great. So we've shown here that 11 is a member of the set Qs because we can do 5 plus 5 plus 1 with rule 3. Cool. So now let's do the same thing for 1c, which is the number 20. How can we achieve the number 20 from the number 8, 5, and the rule that a plus b plus 1 is equal to c? Do you guys know?
5 plus 5 is 11, and then 11 is 8, plus 1 is 20.
Exactly. We can just use what we've did here. So just copy this exact same derivation, and then add in, I believe this was rule, oh, my bad. This was rule 2. This was rule 2. Yeah, we can use this exact derivation plus rule 1, which just says that 8 is a member of Qs. And we can, at the end, use rule 3 again to show that 5 plus 5 plus 1 plus 8 plus 1 is equal to 20. Or in other terms, 11 plus 8 plus 1 is equal to 20. So that derivation is going to get really hard and really long, and we'll be losing time. So instead, I will show that here from the answers. Yeah. See, the same thing here. We just take this derivation that we got in 1b, and we apply rule 1 again using rule 3. And so we get 20. Yeah. Cool. So now we're going to get to 1d. Write down the inductive reasoning principle for Qs. That is, if you want to prove that for one property P, for all A in Qs, we have property A. What would you need to show? Okay. So now, as we've said before starting this class, we would be using principles we learned in previous classes. And one of those principles is the inductive reasoning principle, or proof by induction. And here we are asked to basically explain how we can prove a property P that we have not defined yet can be proven to show that it holds for the set Qs. So you guys know how to do proof by inductions. So what are the trivial steps in proof by inductions? There are 3 steps. Do you guys know?
Base case.
Yeah.
Inductive hypothesis.
Yeah.
And inductive step.
Yeah. Base case, inductive hypothesis, and?
Inductive step? Or
Yeah.
recursive step?
Yeah. Or inductive step, recursive step, inductive step. We just need to do these steps ourselves. Yeah. And this goes for the homework as well. In the homework where you're asked to show the proof by induction, you need to clearly show the base case, the inductive hypothesis, and the inductive step. Yeah. And in our case here, we look at our set Qs, and it is made out of 3 rules. The fact that 8 is in it, the fact that 5 is in it, and the fact that this rule applies. So if we want to prove that a property P is true for the entire set Qs, all we need to do is just look at the elements of Qs and see if the property holds for that. So the reason is pretty simple. For a given property P, if P holds for all of our rules, so that is rule 1. If P holds for rule 1, if P holds for rule 1, right, which is that P of 8 is true, is valid. Right? And we just apply this same case to all the rules of our set. So just copy this for rule 2, which is that property of 5 is valid. And we also apply the same thing for our final rule. But that's the hardest one. Because here we just have the elements by themselves. We can just say that if PA is true, then it holds for rule 1. But for the inductive step, we need to apply, we need to create an inductive step within that inductive step. So that would be where we need to show that if P of, let's say there's an A, P of A, P of B is true, where A and B are elements of Qs. Right. Then we need to prove that A plus B plus 1 is equal to C is also a member of Qs. Yeah. Okay. Exactly. And if we were to open it in the solutions here.
Wait,
yeah.
Don't we need a property of A plus B plus 1 equals C? Or is that?
This property here? Yeah.
Do we need to prove like the
Yeah.
property?
So in the proof by induction, we assume that the property holds for a given n or a given k. And then you just prove it for one step above that, right? N plus 1. So here we would be, like, which is the next question actually. We'd be proving that, would be proving that this equation holds as well.
But
Is that
what
clear?
about the property? Aren't we proving the property holds for the rules?
Yeah, we're proving that the property holds for the rules, and we have 3 rules. And we've shown that it holds for 8, or rule 1. We've shown that it holds for rule 2. And this is rule 3. Right. Okay. And for E, instead of, I realized, running these out and losing valuable time, let's just reason them out. So let's go to the next question. Yeah. So prove that for all A in cubes, there exists I in the elementary integers such that A is equal to 3 times I minus 1. Yeah. So here we'd be applying our proof by induction again. So what would our base case be here? Yeah. Any ideas? Yeah. Okay, so then we can write it here. As we're doing our proof by induction here, we would be basically proving the fact that our property A, which is, this is getting quite messy. Let's just do this for E. We'd be showing that A, first of all, is equal to 3 times I minus 1. We would be doing a proof by induction on this fact right here, where the property of A is such that there's an I, there exists a given I that is a member of the set of integers. So that's what the Z stands for, set of integers. And we'd be doing a proof by induction on this fact right here. And again, to do this, we would need to go back to the rules that we've defined before, which need to hold for the property that we're asking to. So if we were to go to our solutions here, actually, let's go step by step. Yeah. So here is exactly what we said. So now we're showing that the property holds for all rules. So here, A is equal to 8. And we are just substituting in. So this would be a proof by construction in this case. So this is like a proof within a proof. So here we note that a is equal to 3 times I minus 1. And we just replace I by 3. And then we'd be getting 3 times 3 minus 1, which is 8. And the same thing for rule 2. And it gets harder for rule 3 here. Because again, this is where the actual proof by induction is, right here. Yeah. So see, here we have our equation from rule 3, which is c is equal to a plus b plus 1, or here as it's written, you can change the variables if you wish. A is equal to b plus c plus 1, where we have to assume, where we say that b and c are members of the element, the set Qs. So here we apply our inductive hypothesis. This is our inductive hypothesis right here. Assume that B property holds for B and our property holds for C, right? Which is just that B is equal to 3 times I minus 1 and C is equal to 3 times J minus 1. And here we do our inductive step. So we have our base case, we have our base case, we have our inductive step or inductive hypothesis, and then we have our inductive step, where we substitute in the equation that we've been given for A. And then it's just a matter of playing with the variables until you get 3 times an integer minus 1. So you might be asking, wait, we got a completely different equation, right? 3 times I plus j minus 1, I plus j. How do we know that that is an integer? Well, we can reason out the fact that I plus j is an integer. And here, our condition is that I needs to be an element of the set of integers, right? So for all integers you have, you can do addition with them. And at the end, you end up with an integer. Not an irrational number, but an integer. And just like that, you note that fact here. You can substitute I plus j with k, such that a is equal to 3 times k minus 1. And then you conclude that the property holds for rule 3 as well, and that the property holds for the set of Qs. Yeah. So this is a question. This is actually my favorite question in this entire piece set right here. Is 2 in the set of Qs? If so, give a derivation proving it. Yeah. We don't need to get to the specifics here, but we have shown that our set Qs consists of the elements 5, 8, and a rule saying a plus b plus 1 plus 1 is also in the set Qs. So that's like a recursive rule. The question is asking us if 2 is in the set Qs. Is there any possible way that we can get 2 from A and B where they're both in the set Qs? Represent an equation like this. Is there any possible way that you guys can think of? Like, what does your intuition say? No, right? What's your reasoning for your intuition? Yeah.
Yeah, so, there's addition, which can never, the result will never be smaller than what you're adding in.
Exactly, exactly. So this makes sense to us when you say it, but to get full credit on the homework, you need to prove it, right? You need to prove what you say. So we need to utilize what we've done in the previous problems, which is we have a property that we need to show that it holds for the entirety of the set Qs. And then we can say that by this property, this case is impossible. That will give you full credits. So what's one property that will help us in determining that 2 can never be an element of the set of Qs? Yes?
An element in Qs is larger than 5, or larger than equal to 5.
Mm-hmm. Larger than equal to 5.
Like all elements?
Yeah, we can even go easier than that. Think even smaller. 3, exactly. Or 4, you know? Can we say 1? If we showed that Why not?
Because then 2 would satisfy it, which is useless.
Exactly.
Yeah.
Exactly, it would be useless. So the smallest number that we can use is 3, or we could use 4. So we just need to prove. So here our reasoning goes like this. 3 is greater than 2. Prove property holds for 3. And then as a result, thus, 2 cannot be a member of the set Qs. So we don't need to do this, but how would we show that all the elements of the set Qs is greater than 3? How would we show that? Can you guys like reason it out?
Same thing. I guess 8 is greater than 3, 5 is greater than 3, therefore 8 plus 3 plus 1.
Will always be greater than 3. Yeah, that's it, exactly. Exactly. Yes?
Can you write out what P of 3 is? Like what this property is?
Sure,
just,
yeah.
You know,
Sure, so in this case,
rigorous.
yeah, in this case, I would say you can define this any way you want. The way that I define this is such that for all elements x in the set cubes, right, period, x is always greater than 3. So you could do that. This is how I would define it. You could say, you could also write always greater than, like if you wanted to define it your way, always greater, let's say. And you could put in the set qx and then comma 3. Right? What does this logically say? This says that this elements of the set qx is always greater than 3. You could do it the other way if you want. This, as long as you define the property that you do, and as long as you can prove it, you can use it. Yeah. Thank you for clarifying that, actually. Now I realize P of 3 is not that clear. And yeah, this makes more sense. Yeah. Cool. So that's question 1.
Sorry, I just want to clarify.
Yes.
Again. So it's P of 3 and not P of x. So basically, you want to prove P of 3 as a property is true for all x
Like-
cubes, or should it be P of x is true for all x?
Oh, maybe it's P of
That would
x,
make more sense.
where x is a member of Qs, right? Maybe is that?
Yeah, that's what I would think.
Yeah.
Well, if you did P of x, how would you add in 3 in there? How would you say, oh, x always has to be greater than 3?
I think you define P to be, like P of x is x greater than 3. And then you want to show P is true for all x and cubes. That would be my interpretation.
Got it. Well, what if I wanted to utilize the same proof and show that your x is always greater than 4? Then you would need to come up with an entirely different, what's it called, property. Yeah. Your way works too.
Okay.
As long as you can write out your acronym and then just explain that property
Okay.
and then prove it, it holds. Yeah. Cool. So now I think we're going to get to more fun part of the P set. Yes. Awesome. So this is actually my favorite part. The class gets even better as you go along, but these problems here make the most sense to me. Yeah. And by the way, for the midterms and the finals, you guys can use all the lecture notes you have and the section notes. So I would recommend downloading all those lecture notes and section notes, saving them in your computer, and then getting the section notes, and then saving them in your computer as well, getting one PDF, right? Yeah.
We're allowed to use our laptops? Right?
Yes, but no internet. But this policy may change. It was like this last year when I took it,
Okay.
and it will most likely be like this as well.
Okay.
Okay, so now we're going to play with small step operational semantics. We're going to show that this equation right here, 3 plus parentheses, 5 times bar, and our store 0 can progress to 3 plus parentheses 5 times O with our store 0 in one small step. So before we go on, let's explain what this is. Okay, so in the first part of CS152, we are playing with abstract machines. And the way we utilize to represent the states of these abstract machines is what we call configurations, right? Configurations. Configurations. And in the language that we use to do this, our syntax would be like this. Our syntax would be an expression and then a store, right? So this is an expression and this is a store. A store would be like what you store your variables as. So if we look back at this equation, 3 plus 5 times bar, obviously we see that 3 is an integer, 5 is an integer, but bar is not an integer, bar is a variable. Right? In basic programming, you can save any variable that you want with any value that you want. So the way that we would save the values of these variables is with our stores right here, which is represented by sigma. Yeah. So now, how would we logically, if I were to just write this down right here, so 3 plus parentheses, 5 times bar. Actually, yeah. And then our store sigma 0, yeah, goes to 3 plus 5 times 0, sigma 0. So before we progress any further, I just want to explain the sigma 0 right here. Sigma 0, we can call our store sigma 152 if we want. But if we want to indicate the fact that our store doesn't change from one step to another, we just use the same, what's this called, subscript, to represent our store, to show the fact that our store has not changed. And here, when we are progressing from the expression 3 plus parentheses 5 times bar to 3 plus 5 times 0, we are not changing our store. Thus, they are the same. So let's just think about this logically. What would bar need to equal to for us to get this expression? Just say it.
0.
0. OK. So then, in that case, in our store, sigma 0, what would bar be equal to?
0.
Yeah. So this is how we show that a variable is equal to a value. 0. Exactly. And now, to show this small step right here, we would need to draw the derivation tree, and that would be very costly, so this is how you would do it. You would use your axiom to show that the variable bar with store sigma 0 is equal to 0. Right? And these rules are in the lecture notes. So you will be asked to do the same thing for the p-sets. So if you want to just see what rules are available to you, you can just see. Yeah, these are the exact same rules on, I believe, lecture 2. Right? Yeah. Yeah, so these are the exact same rules that we're using to do this. Yeah. Does this make sense to you guys? I could draw it on if you want, but if it makes sense. Okay, cool. Awesome. I can use this, yeah. Okay, so let's do B now. What is the sequence of configurations that this expression right here steps to? So let's also logically think about this. Okay. So let's write this expression. Foo. And I'm going to explain what this is equal to 5, semicolon. Have you guys seen the semicolon before? Of course, yeah. Foo plus 2 2 times 7 sigma 0. Okay. Just to make it more clear. Cool. Okay. So when you guys look at this expression right here, we see that the variable foo is being assigned the value 5. And then we have a sub-expression here showing that the variable foo plus 2 times 7. So you get a value right here. So just to think about it logically, if foo were to equal to 5, what would this be equal to?
7 times 7 is 49.
49, yeah. But the question is asking us to show all the steps that occur. So we don't need to show the derivations right now, thank God. We just need to show what the operations we do until we reach the final configuration. And final configuration meaning you can no longer progress into further steps. What would be the first step we do in this expression, guys?
This is assignment. So does that mean that you change the store? Is that it? Or
Yeah. You
like such
Yeah.
that foo equals 5?
So I believe the way to say it is you obtain a new store where it's your old store plus the fact that the variable foo is equal to 5. And the way you represent this, if I were to just say equal to, here, we are left with foo plus 2, so now we get rid of this. And this is one of our rules, by the way, guys, right? Which,
Assignment.
yes, the assignment rule right here. Or this, sorry,
Second.
this one, right? Yeah, exactly. So see, here we're assigning a variable x, and then, yeah, we represent it like so. So if we were to go back to a problem, yeah, foo plus 2 times 7, and with sigma 0, make sure it's the same store on LaTeX, because when you copy paste, you sometimes, I've forgotten to change the subscript, and I had to talk to my TF and, get it fixed. Foo is equal to 5. Yeah. So what's the next step we would do then? Yeah. By the way, this is ASG2. Right here, the way that we show this is like so. ASG2. What would be our next step right here? Parentheses foo plus 2, close parentheses times 7.
Is this the multiply rule?
No.
Or do we do the inside first? Oh.
So in math, you can't do foo plus 2, right? You have to have an integer plus another integer to add to. So what rule here do we need to use to do just that? So just a second ago, we saved a variable foo's value to be 5, right? So now we need to replace foo with a number. Which rule do we use?
var.
var, exactly. Because what does var do? X is a variable, right? And here, var is just an axiom that says if you have x, and in your store, x is equal to n, then you can do one small step to end with the configuration n sigma, where n is the value of x, right? So you need to show all these steps. That's what the purpose of the small step. Yeah, sorry, before we do this, 340, okay. So var, I know, it's tedious. So you just have to show each single step. And if you miss one, then the entire, when you're drawing it on the midterm or when you're drawing it on the homework, if you miss even one small step, then somewhere along the tree, it stops making sense. And then you realize, oh, I forgot this one thing, and you have to copy paste everything. So then we just do 5 plus 2 times 7. And your store doesn't change, by the way, right? Because let's look at our var here. Does it change the store in any way? Right here? No, right? Do we have a axiom or inference rule where we do affect the store?
Assignment.
Which one?
Both.
Both, exactly. Because here, assignment 1 goes from sigma to sigma prime, right? That's to show that a new store has been obtained. And here we explicitly show we have sigma before, and now we have sigma with the fact that x is now equal to n. Yeah, so we still keep it as sigma 0. At this point, if you get tired of writing this value, you can just say, okay, sigma 1 is equal to sigma 0, parentheses foo goes to 5. So let's do that just for demonstration's sake. So let's write here that sigma 1 is equal to sigma 0 with the fact that foo goes to 5. So now we don't have to keep writing the same thing. 1, yay. Awesome. And we should look at more problems as well, so let's just reason out what this goes to. What would we do now with this expression? Parentheses 5 plus 2, close parentheses, times 7. What's one step?
Addition.
Addition, right? So what does it become? 7 times 7. Sigma 1. And what then?
And then final multiplication.
Yeah. 1. Okay, what's the next step?
I think that's it, right? Or, yeah, that's it.
That's it, exactly. Yeah. This is the final configuration. So we are done. Or in geometry, they like to draw a square for some reason because they're weird. Okay. And yeah, that's it. You just need to do this on the problem, on the homeworks, and on the midterm, and on the final, and you'll be good. Awesome. Let's progress. Okay, so 2C asks, find an integer n and store sigma prime such that the expression that we're given leads to n comma sigma prime. So here we have this big mess of an expression, right? Before we do anything, what do we understand from what we're given here? Here we're given an arrow with a star. That shows that we've applied multiple small steps, one after another. Yeah. Be careful of the star and the arrow versus just the arrow. In the future, we'll be seeing, we'll be seeing large step over relational semantics, which is basically the same thing, but not quite. So here, arrow star shows us that after multiple small steps, we end up with n sigma prime. And in the beginning, we were given sigma 0, and now we're given sigma prime. This means that our store must have changed over the course of doing these, over the course of evaluating our expression. And we end up with an integer. It's not x, it's n. As a result, we need to evaluate this expression to the point where we end up with an integer. And if we end up with a variable, then we've done it wrong. Yeah. So since the steps for this are very tedious, let's just go to the solutions. What would be the logical step to do first in this equation?
Let's start from the inside. So
Yes.
assign 4 bar.
Exactly. So what would bar be equal to? 3. And then what?
Foo would equal 5.
Okay. Here. So
change the store, I guess. Right?
yeah. So here we have bar is equal to 3, colon equal to 3, and then we just have semicolon of 5, right?
Yeah.
So once I've saved the fact that bar is equal to 3, what would happen to this expression? What would this be equal to right here?
Just 5.
Just 5, right? Okay. And then foo would be equal to, as we said,
Would be 5.
5.
Yeah.
Cool. Yep, exactly what you said. Oh, no, wait, this is the previous problem. Yes, equal to 5. And then what? What's our next step in this equation? Or in evaluating this configuration?
Just the 1 bar, or like the 3 gets substituted in, I guess.
Exactly. Do we change the store?
No.
Okay.
And
What then?
We do the addition
The addition,
of 1 plus 3,
yes,
and then the addition of 6 plus 4.
exactly. Does the store change?
No.
Oh, and then?
Yeah, and then bar gets substituted in.
Exactly. And then?
10 plus 3 then becomes 13.
Exactly.
2, and then 1 more substitution.
Yes,
And another multiplication.
yes. That's it.
Yeah.
And that's it. And now we checked. Did we end up with an integer and a change store? Yes, we have. And notice we've had two different stores here. We've had sigma 0, where there are no variables saved as with their values. And then we've ended up with sigma store, and then bar goes to 3. And then we ended up with sigma store, bar goes to 3, and food goes to 5. These are all different stores right here. Yeah, awesome. So any questions on that? Let me check the prime cast. Okay. Okay, and D. Is there, I'm so sorry. Is the relation reflexive? Is the small step relation reflexive? Is it symmetric? Is it anti-symmetric? Is it transitive? What would be your guys' first guess in this?
I'm not really familiar with most of these terms.
Reflex. Oh, really?
Try to define.
Got it. So reflexive.
Except for transitive. I think I know what transitive is.
You know what transitive is? Yeah. So reflexive, I believe, is when, let's say, you have a number A, and I believe if A is also equal to A, then that's reflexive. Am I wrong? One sec. Oh, right. No, I need to say this in a proper way, not the way that I remember. So here we have relations, and there are certain qualities of relations, such as reflexive, symmetric, and transitive. A relation is symmetric or reflexive when, no. When in that same relation, you can have, let's say, a variable x, right? Then, let's say after one small step, you can have x again. So is there any possible case where you have, let's say, a configuration, E, and then sigma, right? And then you, after one small step relation, you also end up with E and sigma. Is this possible? Exactly. Therefore, the small step relation is not reflexive. How about this? Give me an equation, a math equation that is reflexive in this case.
So 5 equals 5.
5 equals 5, or x equals x, or x equals y, I believe. Right? Equals y.
Why would that be reflexive? I don't know.
1 is equal to, it's like, if you have 1, then 1 would equal 1.
1 is reflexive in and of itself.
Exactly.
Because when you small step it, it's like, or is it small step? I guess if you evaluate 1, the result is.
Actually, I'm afraid not.
Okay.
So let's look at our rules right here. I don't think there is a axiom or inference rule that allows us to have the exact same configuration.
Right, yeah.
So yeah, it's not reflexive. A symmetric relation is such that, I'll just erase all these. Okay, a symmetric relation is when, let's say you guys have the configuration x, I shouldn't use x because it's a variable. The configuration A just represents E and sigma, go into B. Let's just say that this relation is valid, right? And since A and B are different, we can assume that there's progress going on here, right? So E goes to sigma, or E and sigma. One small step, let's say the expression is different, right? The expression always changes. But the sigma can be the same or not. So let's just say that in this case, the store is not changed. Now, we have this as accepted. Can there be any possible case where this relation is true, guys? Right? So we have this. Can there be any possible case in which this is true? B, one step, small step, go into A. Is there any case when you can do like a reverse? No, right? So just to look at our rules again, yeah, there's absolutely no case. You always have some sort of progress, some sort of forward progress. And as a result, this is not symmetric. Boom. What else did the question ask for? Yeah. Okay, let's just, for time purposes, continue. Yeah, actually, let's just do transitive as well. The transitive property is the same thing. If you is similar to symmetric, but then you have a third configuration, let's say C. So if A goes to B, B goes to C, then A can go to C, right? So let's. It is.
With the stars too.
One sec. No, my bad. It is actually without the star. Yeah, because you're just doing one small step. Yes, exactly. So what would your guys' intuition be? Would the small step relation be transitive?
I don't think so.
Seems no.
Well, by like, we kind of, I think maybe we can work backwards and be like, because A to C is a small step, it can't be broken back into two small steps, maybe.
Yeah. Yeah. So we learned about small step star, right? Small step star is when you apply multiple small steps. If this were to be a small step star, then that would be true, right? You just apply this, and boom, you get a small step going to C. But since we explicitly said that this is not a small step star, there's absolutely no way in which we can go from a configuration A to a configuration C when, with one small step, when all we can do is go from A to B with one small step relation and go from B to C with one small step relation. We need two small step evaluations, not just one. So it's also not transitive as well. Yeah. Okay. So now large step semantics, which is even better, because now instead of doing the tedious like steps, you can just evaluate the expression to the end. Okay. So okay. Show a derivation that 3 plus 5 times bar sigma goes to 3 sigma. So for time's sake, we can just reason this out. Yeah. So what would bar need to equal again for us to get 3 and sigma 0? 0, right? Because 3 plus 5 times 0 is equal to 3. Yeah. So the derivation that we would need to do here, if we were to just go down, is to now draw this even more messier tree of a derivation. But see here, we should point out one thing. Let's look at the large step derivation of this and then compare it to the small step derivation. So let's look at the small step derivation again. Where is it? It's only here somewhere. Oh yeah, here it is, right? The small step derivation is such that we have bar going to 0, and then 5 times bar, 5 times 0, and then 3 plus 5 times bar going to 3 plus 5 times 0. But this is completely, this is completely different than this. How do we get this derivation? We need to look at the large step derivation rules, which are not here. They are in lecture 4. Oh my god. Yes. Here they are. So we apply the same logic. We learned about axioms. We learned about inference rules. And we need to apply these same axioms and inference rules in our derivation.
Sorry, what is that first rule again?
this int large. So do you guys remember how our small step relation was not reflexive, right?
It is.
This is,
Now
right? Yeah, now it's reflexive, right?
What is the point of that? I can't think
Of that?
would be. It feels kind of like you could add infinite number of these and
Yes.
never stop.
No progress.
Yes. So let's look at why they've used it here. So here we have that same thing, right? We have int large just doing the same thing for this case, just for that case. And then here on the right, we have a variable substitution going on, right? And this would be equal to this right here, var large.
So I guess it's for simplicity. Because otherwise you could, because I guess in the small step for
Yeah.
add, they assume that they were numbers, but here they assume they're.
It's
Okay.
to satisfy. It's to satisfy
Okay.
the condition.
That
right?
makes sense. Okay.
Satisfy,
That's interesting.
yeah, the premise,
Yeah.
right?
That makes sense. Yeah.
Exactly. So here it says expression 1 sigma, large step going to n1 sigma prime prime. So here it shows that the sigma has to change. No,
I think maybe it allows you to like change an expression into a number.
it allows you to. Yeah, I think that's the point. But it sigma can equal sigma prime prime, I believe. Yeah, or else it would have said in the side premise here, sigma cannot equal sigma prime prime, right? Since it does not say that, we can assume that it can. So, to answer your question, the reason why we need int large is so that we can satisfy this condition here. Yeah, of course. It's the same thing for this. Yeah, so which rule do we use here then? 5 and bar, 5 times bar going to 0. Do we use add, multiple, ASG? Multiplication, right? Yeah. You don't need to write the name of the rule this time. And here, yeah, we do the same thing of just int large. And then at the end here, we do an addition, right? Go into that. So, but look at this. In large step semantics, we still had to derive this step. Do you guys see that?
Yep.
We couldn't just do this by itself as an axiom. We had to do it as an inductive step, inductive rule. Yeah. And that's because our rules right here don't allow us to progress on further. So we couldn't have done, oh my God. This is getting ready. We couldn't have done addition and a multiplication in one large step. We still had to use multiple derivations for that. Yeah. Cool. Okay. So now we look at B. Find an integer n and store sigma prime such that this expression, foo is equal to 5, semicolon, foo plus 2 times 7 goes to n sigma prime. Yeah. So let's write this down. Go on to 5. And then foo plus 2. Times 7. Sigma prime. Right? It's just that. Sigma prime. This is the large step semantics derivation going to n and sigma prime. Just to do that with better handwriting. Okay. Cool. And of course I forgot this part right here. Yes. Okay. So, what would your guys' intuition say about this? We need a different store, and we need a value for n to result in. So, can you guys just, without doing derivations, just on paper, mental reason out what n would equal to and what sigma prime would equal to? By the way, our store here could have variables equal to other things, so we can't just assume unless it's separately and explicitly mentioned that everything here is equal to 0, which in this case, on top of question 3, it does say that. But if we were to assume that sigma prime can be other things, we have to define sigma prime in relation to sigma 0. So how would we do it? What would n sigma prime be equal to?
49, and foo is set to 5.
Yeah, so n is equal to?
49.
49. And, so you guide my hand. How would I define it?
Sigma 0, open bracket, foo dot equals 5.
Yeah.
Or arrow equals, oh, arrow, yeah. Right.
So yeah, that's it. And then of course you need to close it. Yeah. This is one large step that we do here. Yeah. If you have time and a big piece of paper, I think we can just look at the solutions for that. Yep, you need a big piece of paper. Here's a tip for you guys, actually. On the homework, this is what I did for my P-set last year when I did it. Let's say you guys have a very, very, very big large step derivation tree, right? Instead of writing out all these rules like separately and then drawing further trees, like, right? And then this expands to further rules, and then that expands to further. Instead of just doing that and driving yourself nuts on LaTeX, do this. Do this. Apply, make it so that, let's say you have a rule, right? Let's say we have the rule, say A, do this. Say A, capital A, is equal to the axiom foo sigma prime large step to 5 prime. Right? And then when it comes down to actually building the entire proof tree, instead of writing out this entire rule, write A, and then let's say B. B would be another axiomatic inference rule. And then C. That's it. And now in your LaTeX solutions, your tree will be way smaller and legible, easy to read, and easier to check. Yeah. Don't bother yourself with building a horse LaTeX. And for me, trying to figure out how to turn the page from vertical to horizontal, like from portrait to landscape. Yeah. Okay, awesome. Yeah. Is the relation large step reflex? Is it symmetric? Is it antisymmetric? Is it transitive? So what did we say for large step being reflexive? And reflexive meant, right, a configuration A can large step to the same configuration A. Is that possible? Yes. So large step semantics, reflexive. Yes. Is it symmetric? Let's think about this.
Yeah, I think it's a necessary condition.
If some things,
If a relation is reflexive, that implies it's symmetric, right? Because you can go forwards to itself and go backwards.
can you come up with a counterexample to the fact that the large step relation is not symmetric?
Oh, I guess. Oh, are you saying it has to hold?
For all.
Okay.
Remember what we did in question 1? We had to show that all the elements of cubes had to
Right.
hold the property,
Okay.
right?
Reflexive is just there exists, but symmetric is for all.
I guess reflexive is a very special case. So that makes sense.
So you guys are both close. The reason why reflexive, the large step semantics is reflexive is because we just have to use that one rule we have, right? Which is int large. Yeah. Whereas I don't think there is a rule here that would, let's say, yeah. So how would you do this? Like, is this possible? Let's say foo, right? Just foo and then sigma. And let's say that sigma has the value foo is equal to 5, right? So this is perfectly legit what I've done right here, right? It's perfectly allowable, right? You're just substituting it. Okay, can you do this? Can you do that? No. So then we were allowed to progress from A to B, but we were not able to progress from B to A, right? Yeah. So as a result, is this symmetric? No. Yeah. Okay. So then,
What is anti-symmetric?
yeah. So yeah, an anti-symmetric, I would define that right here. Let's do it right here. Okay. So we would define anti-symmetric as, let's say we have A and B again, right? If for our relation, large step, if A large step B is not possible, and B large step A is not possible, then the relation is antisymmetric. Or a better description of this would be substituting the large step relation for just any relation that we have, right? That relation could be addition, multiplication, small step, large step. So for relation L, or relation R, let's say, if A R B and B R B don't work, if they just don't exist, if they don't exist is a better way of saying it. Yeah, then R is anti-symmetric. Or, I'm sorry, it is. Wait, am I confusing this? Yeah, it is, my bad.
So does that mean the small step relation was anti-symmetric?
So let's think about this.
We might skip that one.
We did. So let's think about this. Can we, for any relation A and B, are we able to go with any relation? Can we go from A to B? Let's say if A and B are equal to each other, can we progress?
In large step, but not small step.
Exactly. In small step, we can't. So what relation did you have in mind there? Like, what values did you have in mind for A and B?
I mean, that example would be good, I guess.
This one, foo 5. Actually, this does exist in small step semantics.
But the reverse doesn't exist.
The reverse does exist, but here the reverse has to exist for both. Yeah. So,
Wait, it has to exist or can... Sorry, if it exists for both, that's symmetric. So if they both don't exist, then that's anti-symmetric. Is that like the... Right.
yeah.
So, converse? Yeah.
Oh, it is so that, okay, here we need to, let's go back to large step for now. We're going to come back to small
Sure.
step, yeah.
So for large step, I can imagine if they're... like you said, if they're both, if it's an integer on
Yeah.
both sides, like 5 comma sigma,
Yes.
5 comma sigma, then that would, then that's possible in both directions. So therefore, large step is not anti-symmetric.
It's not anti-symmetric, exactly.
And it's also not symmetric.
It's not symmetric as well, no.
Yeah.
So let me ask you a question. Did you use the fact that it's not symmetric to conclude that it's not anti-symmetric?
Not necessarily, because
Yeah.
if you use the, I guess the small step is an example where it's not symmetric, but it is anti-symmetric, and large
Yes.
step is an example where it's neither.
Actually,
is it?
So yes, so the small step relation is where it is not symmetric, but it is antisymmetric.
Yeah.
And the large step relation is where it is neither symmetric nor antisymmetric. So here we can conclude that just because a relation is symmetric, it's not antisymmetric.
Okay, cool.
Yeah. Mm-hmm. Okay. Yeah. Are there any problems left? Okay. There aren't problems left. So in the remaining time left, do you guys have any questions from the P set or from the class or how the class is run? Format of the test?
Sure, why not?
Okay. Last year and in the previous years, the midterm and the final have always been multiple choice. So yeah, multiple choice. But it's no piece of cake. It's multiple choice, and it's open book, open computer, no internet. So you're allowed to use all the lecture notes, all your homeworks with you. I believe this year Professor Chung mentioned something about adding in some like short response questions in there, but it will almost definitely still be open everything.
Would it need a large piece of paper to write out the derivation of axioms?
Yeah, I think he will give you enough space to write your rules, or you can use the same tactic that I just showed you. Yeah. And other than that, the P sets are of course every other week. And usually the office hours when the P set is due, like that week, always gets really busy, especially towards the end. So I would suggest hitting up office hours that are not at night, but usually during the day, because usually those get less people. Yeah. And when you're submitting your assignment to Gradescope, make sure to not include any identifying information in pages like 2 and down. You should only include your like HUID and your name and who you collaborated with. So you guys can obviously talk to each other, collaborate, but the answers that you write in your PSET like should be your own, and the code that you write in your PSET should be your own. But again, you guys are of course allowed to like exchange ideas, reason out topics and issues. But if it comes to a point where you guys are saying, okay, the answer is 8 small steps, sigma, like that would be a violation of the honor code. Yeah. And I believe the midterm is the week before spring break, I believe. Yeah, so you guys don't need to worry about a big midterm coming up for spring break. And usually it's not that big of a stress. So as long as you have the lecture notes, you should be fine. However, if we reason out the fact that professor is letting you use lecture notes, then we can say that lecture notes by themselves will probably not be enough to make up for, let's say, you knowing or not knowing the material, right? So actually I found, and from talking to other people from previous years, I found that we rarely use the lecture notes while doing the midterm and the final, because it's just a waste of time. And when you're scrolling through like 70, 80 pages of notes, yeah, it gets pretty unproductive. Yeah. Any other questions?
And the first piece set, we probably have all the material needed for the first piece set already, right? Or are
Yeah.
you still learning stuff?
For the first piece set, have you guys seen IMP yet?
Yes, today.
Today, okay. Then let me check real quick, actually. It's a good question.
We also need coding somehow for that.
Yes. Actually, no. For PS1, you don't need to do any coding. That's a way for you to check your answer. For homework 2, you do need to code in OCaml.
What's the coding like? Do you know?
It's just like CS51 coding assignments, except it's got more of a focus in implementing the small step and raw step. You're reducing. Yeah. Let me check actually that real quick. Yeah, I believe IMP is the last topic here. Give me one second, please. Homework promise. Here somewhere. Where's homework 1? Is this it? Yeah. Yes. Oh my god. Okay. Proof by induction, stack-oriented programming.
There's that question about the tree as well,
Yes.
which is induction.
Yes. Let me go up real quick. Yeah, stack-oriented programming. Yeah, see, this is where you
Right.
use a property. Exactly.
And then,
Yeah.
so the stack-oriented programming, is that based off IMP stuff then?
This is based off imp stuff. Yeah, you're not writing OCaml code here.
Okay.
Yeah. And see, like in the previous question that we did, the one related to the inductive proof,
Okay.
it's very similar question.
Yeah.
So you just use the same
Right.
logic to do.
Great.
Yeah. Okay. Great. Thank you guys.
Cool. Thank you.
Thank you.